Hi, my name is Molly Chabra, and I'm a sophomore at Mason High School in Mason, Ohio. So this year, I worked on creating a shoulder joint replica to improve PPG sensor signals in hypertension monitoring. So I wanted to do this project because over the past year, my dad has ordered so many different smartwatches online, just trying to find one that will accurately measure his blood pressure while exercising. So, a little bit of background about hypertension. Hypertension is also known as high blood pressure, and it's a common condition that leads to heart disease and strokes, which are the leading causes of death in the United States. And only 3/4 of the people who have this condition do not have it under control. So, that means it's becoming a big problem, especially in the US. So, hypertension is known as the silent killer, meaning that it needs to be measured over a longer period of time. And those one time measurements at the doctor's office, and that too only once or twice a year, is not sufficient, bringing a need for continuous monitoring. So, a current solution that has come up are wearables for continuous monitoring. So, how this works is a smartwatch, it will measure your PPG signal, where a common PPG signal graph looks like this, where the systole are the points where your heart is pushing out blood, and the diastole points where your heart is at rest are all measured. So these points will be continuously measured over a longer period of time, measuring and detecting things like a morning surge or a sudden blood pressure spike. Now, of course, wearable devices have their limitations, motion artifacts. Like seen in the video, motion artifacts are artifacts that distort PPG signals from any sort of body movement while doing daily activities. As you can see in this video, as this man does a simple motion such as jogging, the PPG graph goes from a clean, low noise graph to having something with so much noise, and the noise constantly increases. Now, this pollution has to be removed, and it's removed through filtering technologies. Now, a lot of filtering technologies cannot do so and remove these motion artifacts accurately, leading to distorted systole and diastole points. And distortion of those points can lead to a possible misdiagnosis or even getting the improper treatments for yourself. So, if PPG signals have artifacts and current filtering technologies have limitations, my overall problem was, how may we create a controlled platform to capture and filter effects due to motion, skin tones, and pressure variations? Now, for my project, I worked with Purdue's Biocom lab, where in lab they had already created this biomechanical arm, but they had no way to create these controlled motions with that biomechanical arm. So I wanted to create a controlled platform, and my part of this project was, how can I create a shoulder joint replica mimicking human motions when attached to a biomechanical arm with artificial skin and arteries? So for my shoulder joint, I wanted it to exactly mimic human shoulder motions, with the most important criteria being that it has 3 degrees of rotational freedom. The other criteria that I wanted it to have were that it should withstand the weight of the heavy biomechanical arm and have a high stiffness and stability for that biomechanical arm. It should be simple, where no parts in these parts are interfering with each other and bumping into each other constantly. It should be able to repeat thousands of movements while testing with using this as a controlled platform, and of course use sustainable and affordable materials so that I can remake this prototype for if there are any errors. So before designing how I wanted the shoulder joint to look, I did some prior research on what mechanisms I could use to perfectly emulate a shoulder joint and follow all my design criteria. I found that parallel manipulators, like shown in this little clip art, have been used in robotics for human-like joints many times in the past. After doing further research, I found something called a spherical parallel manipulator, and I narrowed my research down to 3 papers, where I selected one, Lee and Jin's design optimized for torque transmission and stiffness. Now, this design, as shown here, it has 3 different limbs, all different colors, and these limbs are symmetrical at the bottom and as well at the top in a triangular shape. These limbs move about point O, where this design balances strength, precision, and feasibility, leading me to my design hypothesis that a spherical parallel manipulator would achieve the design goals of the current research. So, as for my design approach, I chose a fairly systematic approach where I began by selecting the base design from the literature review and designing each of the parts and assembling them on a CAD software called Fusion 360, where I then tested it on that software and tested it at the Biocom lab as well. From here, I began sketching the design that I would ultimately model on CAD software as my shoulder joint prototype. My first design was very similar to the spherical parallel manipulator in my literature review. It included the 5 main components, but I found that this design does not have 3 degrees of rotational freedom like I wanted it to have. So I began researching more on different types of SPMs, and I found a similar one where they used rotational drives. And I decided that since this rotational drives meant that this would have the rotational drives made sure that the joint would have 3 degrees of rotational freedom, so I decided for those rotational drives, I can replace them with gears. My next design shows that these gears that replicate those drives are stacked into what I call gear levels. Now, each of these gears attaches to the limbs directly, but I found that in this prototype, there was no way to move each individual gear. So I created a base drawing where I would use that original design where I have 3 motors all in this symmetrical triangular base, where each of these gears would connect to what I call driving gears, and these driving gears each of them move gear levels. Now, a problem with this was I had to find a way for the gear to move the limbs without them interfering with the driving gear. So this leads me to my gear mechanisms. Now, all of these all of these levels, they all stack on top of each other, where they're drawn to fit, and as you can see, at the top of each of these gear levels, that attaches to what I call gear rims. Now, only part of the gear rim is shown, the rest of it connects to the limbs, but it creates this mechanism where nothing is interfering and each level moves a different limb. So this leads me to my final design, where after sketching out my design, I modeled each part on Fusion 360, where each part was iterated around 17 different times. Now I assembled all of the parts in the software to create this overall SPM. From here, I identified any potential design flaws with tolerances or anything else, and conducted a motion study to ensure that all my design criteria were met. From here, I performed finite element modeling to understand how my design would do under different loading conditions. For my simulation setup and my static stress analysis, I wanted to test the distribution of different stresses and deformations under 2 different static loads, 0.5 kilograms, which is more like the weight of the biomechanical arm, and 1 kilogram, which is similar to the weight of the biomechanical arm plus skin and arteries. So for structural buckling analysis, I wanted to predict what load it would take for my structure to fully buckle or permanently deform. So as for my setup, I made sure that the weight of the biomechanical arm would be set to be at the top, and once that load is attached to the top, any of these circular points or this cylindrical points over here, all of those would be able to rotate when that load is attached. As for my material, I chose polylactic acid because it's more sustainable than other plastics, and I chose low and high strength because of plastic's directional properties, so depending on what angle it's printed at, 3D printed at, some areas may be low strength, some may be high strength. From here, I ran a total of 8 conditions. So these first 4 conditions showed static stress for low strength and high strength PLA for 0.5 and 1 kilogram forces. So as you can see, all of the limbs in these conditions are this dark blue color. And in the dark blue color on this color graph, we can see that dark blue is at the lowest stress. So that means that not only was this stress equally distributed among all 3 limbs, but the stress that was applied to these limbs is also significantly lower than PLA's yield stress. You can compare this as 0.01 megapascals versus 26 megapascals, which is a crazy difference. For my next condition on total displacement, once that load was attached, the displacement was only around 1 micron. So that is a pretty insignificant amount. As for contact pressure, it was only at these 3 points where there was only minuscule contact pressure, around 0.17 megapascals, also a pretty insignificant number. When the load was attached, there was also negligible buckling, so my limbs stayed very, very stable, and I would need around 1,000 times more of that load for my structure to fully buckle, meaning that my structure in all the tests stayed stable. Next, before I went to the Purdue's Biocom lab, and I 3D printed all of my parts and assembled them at the lab. So with the assembly, I attached all 3 motors to the base of the spherical parallel manipulator and programmed it using Arduino controllers as seen in the video. So in this video, you can see that moving platform at the top. It's moving in all sorts of different angles, emulating that human shoulder movement and creating that 3 degrees of rotational freedom, just like a human shoulder. From here, I ran one more thing and tested that biomechanical arm attachment for stability on top of the moving platform, which it proved to be very stable. So some challenges I faced through this project were ensuring that I had the correct dimensions and angles when modeling this on the CAD software. I had to make sure that many different parts were the same angles, and I had to create over 20 different iterations for some of these parts. Then I had to avoid interference between the limbs and ensure smooth movement and that all my design criteria were met accurately. As for nonlinear kinematics in CAD software, I had to make sure that none of these parts are clashing into each other at points called singularities, and I had to make sure that some of these limbs were only moving 60 degrees, some were moving 90 degrees when controlling it. So in conclusion, I had a successful design, building, and testing of my SPM prototype, where it accurately replicated human shoulder movements with high fidelity and validated design robustness under real loading conditions. But of course, every experiment has its drawbacks, and I would need a further scaling and optimization because of the torque limitations of the motors and gears. So basically, everything has to be scaled up, and strongers in motors and gears need to be used. So as I mentioned earlier, motion artifacts are a major challenge in PPG blood pressure monitoring. Current filtering technologies struggle to isolate these artifacts accurately due to the randomness of human movement. This reduces the reliability of continuous monitoring. This is where my shoulder joint replica comes in. By using my controlled platform, I can generate precise, repeatable motions, which allows me to isolate the exact factors causing motion artifacts. Unlike human motion, which is unpredictable, this platform enables me to produce clean, reliable datasets for filtering algorithms. So what I would do is leverage my controlled platform to generate motion datasets with thousands of human motions that match up with human activities. From here, I would use that dataset to develop AI models which filter out motion artifacts in PPG signals. And I would also test this PPG algorithm in wearable devices, just like my dad wanted to do. So as for my project, I'd like to thank Dr. Ward for being a great advisor, Haley for being my mentor, and McKinley Educational Initiative and Purdue's Biocom Lab for funding this project. Here are my references. Thank you for listening to my presentation.